Hello and welcome to episode 6 of How to Code a Game Like Minecraft in Unity. In this one we're going to cover basic character controller and we're going to do it without physics colliders and I will explain why in a second. Before we get into it, we just need to do a couple of little changes to our scripts, to our script world CS. The first one of which is we're going to need our player to be spawning inside the world. Right now we've got him spawning 2 blocks above where the world actually ends in terms of voxel data. So we're just going to set this to -50 for now. That puts him well inside the world. Now the other change that we're going to need to make is, I'll just to remind you where we left off. If I press play, we got our chunk generation working properly and spawning, but it's not very optimized at the minute. So when we generate new chunks, it's quite laggy. As you can see, it stutters every time it generates new chunks. It's fine once the chunks have already been made, but when it's generating new ones, it's not the best. We are going to deal with that, obviously, but I'm very conscious of these tutorials being quite lengthy as it is, so I don't want to deal with it in this video. So what we're going to do in this video, because we're doing the character controller, we don't need the world to carry on spawning around the player as we're going. So we're just going to get rid of not get rid, we're just going to comment out this part for now. And all that's going to do is it just means that we're not going to be generating new chunks as we move. We still, if you recall, we call our first generate world script once at the start. So we're still going to get our world, but now when we move around, that world will not change, basically. It's not going to generate more chunks as we move around like that, which is fine for what we're about to do. So, first things first, physics colliders. The most simple way we could go about this is if we were to use physics colliders, and basically we would put some collider meshes on our chunks, we would put a rigid body on our player, and we would be ready to go. So I will just quickly show you what that would look like.
A few moments later.
So I've just imported the Unity standard assets into our project just for the sole purpose of getting hold of the FPS controller. So we're going to pull that FPS controller in here. We're going to go into our world and set our player to the FPS controller. We'll just disable the main camera for a second. And then if we hit play, we're going to have a player that will fall through the world, basically. There we go. And that's because we've got no colliders on our chunks. Our chunks are just mesh data. There's no physical substance to those chunks at the minute. So we can fix that by going into our chunk generation script. And when we create a chunk, we're going to, well, first off, we need a mesh collider. And then in here, we add our mesh collider. And then to set our mesh collider, we can, because this is just a quick slapdash way of showing you it working, we can just go mesh collider dot shared mesh equals mesh filter dot mesh. Now, the reason that we're not going to do this, it takes longer to load. It's not that big a deal right now because, well, it's only a one-off load. But when we're actually generating these chunks on the fly, when we're generating them as we move around the world, it's a bit more severe. And it's going to be, and basically we want as much optimization as possible. So if you're happy to use colliders in this sense, by all means, stop the video here. You've got your basic character controller. Just drag in the Unity standard assets first person controller, slap some collider meshes on your chunks, and you're ready to go. Like I said, this is going to cause problems though, especially when you start editing chunks, when you start destroying blocks. So we'll just reset back and we'll do it the way that I'm going to show you how to do it next.
12 seconds later.
So I've reset everything back to how it was before we started messing with mesh colliders. And now we're going to do things the slightly more difficult way, but a way that is going to make things a bit easier when we start having to mess with chunks through the game on a regular basis. Because if you think about the way that this is happening, the way chunks are created, every time a block is modified, that whole chunk has to be redrawn because it's one mesh. Even though you've got the data, you don't have to go through and get each voxel individually again like you do when you first generate the chunk. You still have to draw that whole mesh again. And if you've got a mesh collider, you have to draw that whole mesh collider again. And the mesh collider is a very relatively system intensive procedure. So drawing a mesh collider with all the physics and everything is a lot more system intensive than just drawing a regular mesh, and you have to do that every time a block is modified and every time a new chunk is generated. So we're not going to do it that way. Like I said, I've shown you how to do it that way. If you want to go with that, by all means, go ahead. If you want to look at this alternative way of doing it, then keep watching. So the first thing we're going to need to do is we're going to create another empty object, and we'll just stick this for now, because it doesn't really matter where we put it, because in fact, yeah, it doesn't really matter where we put it, because it's going to get moved by spawn when we generate the world. And we're going to call this our player object, and we're going to drag our camera into here, and it wants to be 1.8, because that's roughly, I think that's what the character height is. So 1.8 is head height. Technically, the character is just less than 2 blocks tall. So that's where our camera is within the player model. There's no colliders or anything, so, because there's no character model right now. There's not really a lot to go on visually, but trust me, I guess you'll see it in action soon. So now that we've got that, we're going to have to drag our new player object, and then if we go into scripts, we can create ourselves a script for our player, and we'll put that on there. And we'll open it. So straight away we can just quickly create a very basic player controller to move around, and the way we'll do that is we're going to need a few values. So float, horizontal, float vertical, and then we're going to want a horizontal and vertical for our mouse. And then finally, we want a vector 3 for our velocity, which is going to act in a very similar way to how velocity in a rigid body would be represented. So then we're going to our update, and we're just going to set these values. In fact, we may as well start as we mean to go on. So we'll have these in our own function. We'll call it private void get player inputs, and then we're just going to set all these values, well, except for the velocity, we're going to set all these values that we've just created at the top. Now, if you don't know what get axis is, get axis calls, I'll just go back into Unity a second. You have your, bearing in mind, I'm assuming that most of the people who are going to be watching my videos are quite beginnery, novice people who are quite new to coding, to use something approaching proper English. So I'm sorry if this is all, fairly simple stuff for you, but I am assuming that most people who are watching this aren't quite as up on things. So you've got your input settings here in your project settings, and these are all the controls that Unity sort of has a reference for, I guess, would you call it. And you could add more references, and you can delete them, and you can change them. So basically, instead of referencing a specific key in your code, so instead of getting if input dot key down key code spacebar or whatever, you could have fire, and then you could tell it that that button is spacebar, so then you'd just reference fire, and then it would know that if spacebar is pressed, that's what that button means. What we're getting right now is the axis of horizontal, which is set to be like the left and right or A and D key. So you've got your WASD or your arrow keys work for the horizontal and vertical axes, and basically it returns a value between -1, in this case horizontal, so -1 for left and 1 for right. And all we're going to do is set our horizontal float to whatever the get axis float is currently at, and then the same for the vertical. And then the same again for the horizontal. But this time it's mouse X. And this one is mouse Y. And then up at the start of our update thread, we will call get player inputs. And then just to show part of it working, we'll just do a quick, we're going to need, right, so first off, we're going to need a reference to our camera. And then because we're only calling it once at the very start, we'll use GameObject.find to get a camera reference rather than cluttering up the inspector. So at the end of our update, we'll use some of these values to set our look position, basically based on what the mouse is. So not rotation. Transform.rotate vector3.up. So we're rotating around the straight vertical up axis, and this is a vector3.up. So this is always straight up, regardless of the orientation of the player. And then we times that by mouse horizontal, and then so that's the player, that's this object, the player object, which contains the camera object. And what that is when we rotate left to right, we want the whole player to turn. We don't just want the camera to turn, because then if you set off walking forward but you've turned the camera to look right, you're going to start walking off to the side of where the camera is facing. So when we rotate left to right, we want the whole player to turn. Sorry, that should be a transform. For the camera, we want to rotate vector3.right. So this time we're going on the right axis, the horizontal. So it's rotating up and down around that right axis. Times, and we want minus mouse vertical. If you wanted to invert the mouse look value, so you wanted it to go the opposite way round, then you would have this value, this mouse vertical, you would have that just be a regular value, not minus value. But because I don't want it inverted right now, I'm putting it as a minus value. So now if I press play, still not much of a character controller, but we should be able to now look round. There we go. And that's all just based on the mouse value. Now these values aren't clamped, so you can technically just go all the way around like that. It's not a massive deal to do, but I'm trying to keep this video short, so I'm not going to go into too much nitty gritty. I'm sure you can figure how to do that yourself, and if not, I can always do a pickup video on it later. So we've got our look video. We've got our look command set up. Now we need a direction for movement. So just to show you everything working, I'm just going to do a very simple direction equals transform.forward. So that's whatever forward is to the player. Oh, sorry, not direction, velocity. So this is whatever forward is currently to the player, whichever way he's facing, whatever that forward is, times vertical. Remember, this is a vertical axis. I know it's easy to think of vertical as like up down. In this case, it means the up down axis of the controls, which is the up and down arrow key or the W and S key, and we're timesing it by that. So basically, transform.forward is in absolute space. Vector 3.forward would be 0 on the x-axis, 0 on the y-axis, 1 on the z-axis. What timesing it by vertical does is, if you've got your key pressed down, then that value is going to be 1. So 1 times 1 is 1. That's fairly straightforward. If the axis was 0.5, then 1 times 0.5 would be 0.5. So it's half the value forward. If it's 0, then it's going to be 0, because anything times 0 is 0. And what that does is it basically modifies our forward direction by the scale of whatever the vertical value currently is. And then we're going to add to that the transform.right value. Again, this is just whatever the current right to the player is, whichever way he's facing, whatever right is, that's what this transform.right vector will represent. And we're going to times this one by horizontal. And then we want to times all of that by time.delta time. And then we'll just times that by 3f to give us 3 float, to give us a nice sort of speed. We don't want to be moving too slow. And then at the bottom down here, transform.translate direction, not direction, velocity. I did actually call it direction when I was working this code out in the first place, and then I decided velocity was a better name. That's why I keep accidentally calling it direction. And then we would need to set our space. Now we want our space to be world, because if our space was self, then it's only going to translate relative to itself, but we want the space to be within the world. So if we go back into our game now, we should be able to move around a bit. There we go. So we're getting there. Now, of course, this is great if you just want to fly around the world, but we need a character controller. So the next thing to do is we're going to give ourselves some values. These will be public values. We'll call this one float walk speed. This is just to get us set up for what we're going to do. And then we want a gravity value. Now we're going to set the gravity value in here. The chances, I mean, I'm making it public so that it is easy to change it in the inspector. If you wanted to change it in the inspector, really you're probably going to, realistically this wants to be a constant value throughout the game, because you don't want different objects falling at different speeds. But just for now, because we've only got one object that's affected by anything, we'll just set it in here for now and we can clean things up later. So the value wants to be minus 9.8, and obviously you can play with this value. The reason it's minus 9.8 is because the rate that things fall on Earth in Earth gravity is 9.8 meters per second. In Minecraft, one block is meant to represent a meter. In our game, 1 unit is the size of a block, so 1 float is the size of a block. That is meant to be a meter. Minus 9.8 represent it. So if we were to move a block by minus 9.8 every second, that would represent actual gravity in our game, about a roughly accurate representation of gravity within our game. And so to quickly show you gravity in action, we'll just add, first off, we'll set this to 3F, and then we'll change this to walk speed. And just to show you gravity in action, we're going to add velocity plus equals vector 3 dot up times gravity, and then we want to times it by time dot delta time, because we don't want to take up bearing in mind this update runs every frame, not every second. So if we took off minus 9.8 every frame, it would be moving a hell of a lot faster than average gravity. So we need to break up that 9.8 per second into whatever it works out at a frame. Bearing in mind that you can get 60, 80, 120 frames per second. So it's going to be quite a small number. And of course now we're just falling through the Earth because, once again, there's no substance to our chunks, so there's nothing to stop us from falling through. So this is where it starts to get tricky. This is where we need to start. This is where it's going to start to look like maybe just sticking some mesh colliders and a first-person controller from the standard assets is a more preferable way to go, because it's going to start to get a bit messy from this point. But bear with me, even if you decide not to use this way, it's probably good to at least understand how it's done. So the first thing we're going to need to do is, in addition to our camera reference, we're going to need a world reference, and we'll get that the same way we get the camera. In our world, speaking of which, we also need another function in here. For now, for the same reason that we disabled our view distance, we're just going to do a very straightforward, simple function, and then we'll integrate things a bit nicer as and when we need to. So the function that we're going to create is a bool function. It's going to work a lot like the in the chunk we've got a function something along these lines. Check voxel. It's going to work a lot like check voxel, but check voxel is specific to this chunk, and we need something where we can just pass any vector 3 or any 3 values, any float values that represent the 3-dimensional coordinates of a voxel. Doesn't matter what chunk it's in, doesn't matter where we are in the world, we want to be able to just pass this value into it, and then it will give us back whether or not that chunk is, there is a voxel in that space. It doesn't matter what the voxel is, we're just interested in whether there is one there or not. So we're going to call this check for voxel, and it's going to take in a float x, float y, and float z. Now the first thing we want to do is adjust our first thing we want to do is put a space there. Is adjust our incoming values to, well, not adjust them, sorry, we need to create new ones because obviously they're floats and we need ints. So we're going to create an xcheck equals mathf dot floor to int, and then we just pass in our incoming float value, and then we do the same for x and y, for z and y. And this basically, well, I've explained this to death in previous videos, but basically this takes in the float, whatever it is, and gives us an integer that will be the lower end value of whatever voxel we're on. So we always get the bottom left corner of the bottom left back corner of whatever voxel we're on. It's just nice and simple and helps us always be working from the same frame of reference. Then once we have those, we need a couple more values. We're going to call this one xchunk. And xchunk will equal xcheck divided by voxel data dot chunk width. And then we're going to do the same for the z value. So now we have our global value for whatever the voxel is in ints, and we have our chunk value in x and y coordinates, x and z coordinates, sorry. So we can pass this x and z straight into our chunks array here and get whatever chunk is there, if there is a chunk there. For the moment, the way this function is set up, we will get null reference exception errors if our player wanders outside of the world space. This is why I moved him lower down at the very start of the video. We can deal, like, we will put in checks to cover this kind of thing so we don't just get errors if something unexpected happens, but for now it's not really important. We'll deal with that kind of thing later. So our final value we need to get is we need to get the value of the voxel within the chunk that it's in. So now that we're passing in a global value, so this could be something like 800 by 50 by 2072. It could be anything like that. We need to reduce it down to a chunk coordinate and then a 0 to 16 or whatever our chunk width is currently set at value within that chunk. So to do that, we're going to change xcheck minus equals and then xchunk times voxel data dot chunk width. So basically we're getting the start value of the chunk, which the left back corner of the chunk, and then we're taking away that times the voxel data from our xcheck value. So if for example there were 2 chunks and we were 8 blocks into our second chunk, so that would be 16 chunks, so it'd be 24. So we're on block 24. We're in the second chunk, which is chunk 1. If we times 1 by chunk width, which is 16, then that leaves us with, and we take away that value from the overall. The overall was 24. X chunk times voxel data dot chunk width would equal 16. Take the 16 from the 24, that leaves us with 8. 8 would be our value within the chunk. I really hope that made more sense than it sounded to me. And then we obviously do the same for Z check. Y we don't need to do anything with, because there is only one chunk up and down, and the Y value is the Y value. We don't need to mess around with it. And then what we're going to return is block types, chunks, X chunk, Z chunk dot voxel map, X check, Y check, Z check. Dot is solid. And this error here is because our chunk voxel map is not currently a public value, which we're going to have to change obviously, because we are going to have to reference this from outside at the minute. We're probably going to change that later though, so that we don't directly access the voxel map array in any given chunk. But so now that we've got that, we can go back into our player script. But we're going to need a few more values. So the first ones we're going to need are I'll add all the values even though we're not going to need them all immediately. But we're going to need a sprint speed. We're going to need a jump force value. I imagine these are pretty self-explanatory what these values are for so far. Jump force is roughly 5. These values that I'm putting in as the defaults, they're not just off the top of my head. I have experimented with these. Now we're going to need 2 more values. We're going to call player width. So if you know how mesh colliders work, and just in general how colliders work, if you imagine a player had a capsule collider on it, you would have to set the height of the player. We know the height is 1.8, because it definitely, you don't want it to be more than 2 blocks. Obviously that would be different if you were doing something like an Enderman, which is about 3 blocks high. But for our player, we know it's less than 2 blocks. We know it's 1.8, so we don't need to really have a height value. But the width, that's something you might want to play around with. But the width would be the diameter of, or the radius of the capsule. No, diameter, sorry. Well, maybe radius would be an easy one to go with, but we'll stick with diameter for now. And there's no default. Yeah, okay. We'll set a default value of 0.3. Bounce tolerance would be a bit easier to explain. when we actually come to use it. And then we're going to need a float down here called vertical momentum. And a bool called jump request. Again, some of these values will make more sense when we actually come to use them. And then finally, at the very top, we're going to need an isGrounded bool and an isSprinting bool. And now we can get into actually coding this mess. So we've got our get player inputs. We're just going to add a little bit more to our get player inputs. So if input.get, we'll use our actual input settings to determine which buttons we're going to press. So what is fire 1 currently? Fire 1 is left control. So we've already got a jump. Jump is space. That's fine. We'll leave that as it is. One of these, I think, fire 3. Right, fire 3 is currently left shift. We're going to use that for sprint. So I'm just going to rename that to sprint. And I believe these ones down here are, yeah, joystick buttons. So I'll just rename that to sprint anyway. We're not really using joysticks at the minute, but that's something you can play around with. It's not really crucial. So we've got a sprint and a jump. So now, instead of using get key down key code dot left shift, I can use get button down sprint. And then if I ever want to change what key, or I want to let the player change what key that is, then I can just change it in the actual project settings rather than changing it in the code. Because if I hard code spacebar to mean jump, then spacebar is always going to mean jump. There's no way the player will be able to change that unless I code something in here to reference every single key that the player might want to set as jump, which is obviously not practical. As I say, most of these values aren't going to come into play straight away. And then if we get button up, sprint. So button down obviously means if the button is pressed. Button up means the button has, you've taken your finger off the key basically. So if you press sprint, sprinting will equal true, and if you take your finger off sprint, sprinting will equal false. And then if isGrounded, we haven't set an isGrounded, we haven't put in a mechanism for telling whether the player is grounded or not yet, but we will have done by the time this comes into play. If the player is grounded, and input dot get button down jump, jump request equals true. And I'll explain why we're using a bool for this when we come to actually implement the jump code. So first things first, we need a way of checking if the player is grounded. Now this is where it gets a bit tricky. We can just check, we can just get a value from where the player is, and then get the voxel value of where the player is, and then check the voxel below them. However, the player is only ever going to get that only ever gets us one value, and the problem with that is the player could theoretically be standing on top of 4 voxels at once. It could be on the intersection where 4 voxels meet, in which case we need to return that the player is grounded if any of those 4 voxels are solid. So we can't just reference it once. So the way we're going to get around this is we're going to create a float. Bear with me on this one. And the float value, what it is we are going to pass in our downward velocity speed. So this value that we create using gravity here, we're going to pass in that velocity, and we're going to check where the player would be once that velocity is applied. If the player is going to be in a solid voxel, then we know that the voxel below the player is going to be solid because he's currently not in a solid voxel, but once we've applied this velocity to him, he will be in a solid voxel. So then what we're going to do, if we find that applying this value would put them into a solid block, i.e. it would put them into the ground essentially, then instead of returning the value that we were passed, because if applying this velocity just leaves them in the air still, then that's fine, just apply the velocity. If applying the velocity puts them into the ground, we want to change the velocity that we're going to apply. So the first thing we need to do is, take in our down speed value. And then we need to do some ifing. So we have our new world dot check for voxel, and then the value we want is transform dot position dot x, transform dot position dot y plus down speed, and then transform dot position dot z. However, that only gets us the one position, and that one position is at the center of the player. We need 4 positions, one for each corner of the bound of the player. Now, you could think in terms of the player might be circular, like a capsule collider, but that doesn't really apply to Minecraft because Minecraft itself is square. So it's quite perfectly fine to just check on the absolute corners of each of the player, player width, using our player width value, player width to one side, player width to the other side, etc. With that in mind, actually, I've been treating this as a diameter. We're going to treat it as a radius because that just makes life a little bit easier down here. So we need to check this 4 times. We'll have 1 minus player width, and then this one also minus player width, and then basically we just want to do this 4 times. So this one will have plus player width and minus player width. This one will have plus player width and plus player width, and then this one minus player width and plus player width. So this checks from the center of the player to the width, whatever we've set the radius of the player to be, on all 4 corners. If any of them return true, that means there is a solid voxel under the player, which will stop him from falling. So if that's the case, then we want to make is grounded equal true. And then we want to return 0. Otherwise, we'll set is grounded equals false, and we want to return whatever we were passed in the first place. Now if we just quickly go up here and put velocity.y equals check down speed the viscosity, velocity.y, in theory we should now hit the floor. And there we go. So we're part of the way there. As you can see, it's working fine there. However, this is only a downward collision detection. If I walk this way, we can walk right on into that chunk, and obviously we don't want that. So we also need to check in front, behind, and to both sides. And this is a slightly different... Well, before we do this, actually, we're just going to duplicate our check down speed, because up and down check is slightly different because of the aforementioned having to check each four corners. That doesn't apply to checking horizontally, like in front, to the right, to the back, etc. But up and down are both the same. So I'm just going to copy our check down speed and create a check up speed. And the difference here is that we're going to be adding our 1.8 to the checking. The up speed itself will be a positive if we're checking the up speed. Sorry, this doesn't want to be 1.8. Oh, this wants to be 2, because the head is at 2, but we want our collision detection to be a little bit above that. So we're checking above that. We don't need to modify is grounded on this one, so it's just return 0 and return up speed. Again, don't need to change is grounded. And all this does is when we check up speed, if it detects a block on any of the four corners 2 blocks above the player, then it knows that basically the player is smacking his head on something. But now onto those front, back, left, right values. So we're going to create a public bool, and we're just going to call it front. And we'll use get and set for this. And inside here, we want to do an if statement. And similar to the 4 points, we need to do more than one check, but this time it's only 2 checks. And the reason it's 2 checks is because the player is 2 blocks high, essentially. So we need to check not just the block directly in front of the player, bearing in mind that the player's position is at his feet. We also need to check the block above that, because the player might be blocked at foot level but not at head level, and then we don't want him walking blocked at head level but not at foot level, but we don't want them being able to walk through that block just because we're only checking at the feet. So again, we're going to use our world dot check for voxel transform dot position dot x transform dot position dot y transform dot position dot z, and then this is the part where we need to change it slightly for the z, because this is front, so we know we're checking in front of the player. We're going to add player width to get from the center of the player's position, which is dead center in the middle of where the player is stood, to the outer edge of the player. And then we're just going to copy that, but this time plus 1f on the y-axis, so that we're checking the same place but 1 block above. And if that comes back true, we return true. And if it doesn't, we return false. And now we want to duplicate this for the back, the left, and the right. And then the difference is where we're checking. So for the back, instead of in front, we're checking behind, so it's minus player width on the z-axis instead of plus player width. And then for the left, we're not checking on the z-axis at all. We're checking on the x-axis, and left is minus plus. And then right is again on the x-axis, and this time it is plus. So now we can go back up to our update, and we're going to break this out into its own function. So we'll just cut this out. I'm going to call this private void calculate velocity. And we'll paste all this in here. And now we can do the rest of our checks. First of all, we want to change, you know what, let's just completely get rid of this because we're basically going to have to rewrite the whole thing anyway. So we're going to have to change the way we apply gravity. So we're going to use our vertical momentum float that I created at the top. Effect, vertical momentum with gravity. So if vertical momentum is greater than gravity, vertical momentum spelt correctly is greater than gravity, then we want to affect it with our gravity. So if you remember, fixed time dot delta time, if you weren't aware, it's basically the same as time dot delta time, but time dot delta time applies to the frame. So it updates once a frame, and whatever the length of that frame is, if you're getting 4 frames per second, the amount of time in time dot delta time will be a lot more than if you're getting 120 frames per second. Fixed delta time, as the name suggests, is always going to be the same interval regardless of what's going on with your frame rate. So anything to do with physics, which obviously we're not using physics, we're sort of creating our own pseudo physics, I guess you'd call it. But anything to do with that you want as a fixed delta time as opposed to time dot delta time, because you don't want the player to suddenly skip through the floor and fall out of the world just because the frame rate dropped and it updated at the wrong time or something. So we're applying gravity using fixed delta time, and then we're going to check our sprinting. I'm just putting some comments as I go, but I'm not going to go silly with it. So if is sprinting, velocity equals, and then we're just going to rewrite the bit that I deleted that I should probably have copied to save time. Times vertical plus transform dot right times horizontal times time dot fixed delta time, and then this time we're going to times by sprint speed and copy that. However, if it is not is sprinting, then we're just going to use our walk speed. So the only thing we're changing here, depending on whether the bool is sprinting is set to true, is which speed we are using. So now we apply our vertical momentum, which is like falling and jumping basically. Oh. Vector 3 dot up times vertical momentum times time dot fixed delta time. So now we have our basic movement. We have falling from gravity and we have moving around from whatever the player is pressing. So now we need to do our checks to see whether or not the player can move wherever we're trying to move him. So we'll check front to back first. And the way we do that, so if velocity.z is greater than 0, that means that we are trying to move the player on along the z-axis in a positive fashion. It might only be by 0.1. It might be almost walking sideways along the x-axis, but if there's just a slight drift off the x-axis towards the front or back, then we are getting some movement on the z-axis. So if it's greater than 0, that means there is some movement on the z-axis, regardless of which way you think you're walking or facing. There is some movement there, and we do need to check it. If that movement is in the positive, if it's greater than 0, then that means that it's to the front. So we need to check the front. And because we're only checking if there's something there, it doesn't matter whether it's front or back. So we can just go, or velocity.z is less than 0 and back. So basically what this is saying is if there's movement along the z-axis and there is something in the way, then we're going to set z to 0. And then we're going to do the exact same thing for the x-axis. And this time we're checking, that's going to be right because it's greater than 0, and that one's going to be left because it's less than 0. And then finally we've got our y. So this one is if velocity.y is less than 0, this means it's falling, then velocity.y equals check down speed velocity.y. Else if velocity.y is greater than 0, we want to check the up speed, because we want to, if it's less than 0, it means we fall and we want to check below us. If it's greater than 0, it means we're rising up, jumping, flying, whatever. We need to check, make sure there's nothing above us. And the only remaining option, the only remaining state that could come out of that is that velocity equals 0, in which case we don't need to do any checking because we're already at 0. So if I put calculate velocity in there, and I press play, we should now, yep, there we go. We have our collide. We can now collide with our voxels. And this is all using no colliders, no mesh colliders, no physics. This is all just checking the player's position against the voxel map. Now there is one thing remaining. Obviously we have our values for our jump, but we never actually applied our jump. So we'll do that now. We need to create a function here. We'll call it void jump. Doesn't need to take anything in, and all it's going to do is vertical momentum equals jump force. So it's making the vertical momentum positive. Is grounded equals false, because if we jump, we're not going to be on the ground anymore. And jump request equals false. And then in our input, we've got jump. If we press the jump button, we set jump request to true. We're going to put a check in here. If jump request, then call a jump function. Now the reason we're doing that is because this is being called in the frame update. It's possible that the key can get missed sometimes. Like you can call a jump function and it just gets overlooked by the physics, by the fixed update. We don't want that to happen. In fact, we need to put these into the fixed update. Sorry. We don't want it to happen, so by setting a bool, we know that the key's being pressed, and it might not get to it immediately, but it will. Like, it might not get to it this second absolute instant you press the jump key, but it will get to it eventually, and it's never going to be like, we're not talking lag of seconds or anything like that, but just skipping one frame because the frame rate's out of step with the physics, with the fixed time. It could be very annoying if you press jump and 2 times out of 10 it doesn't do anything. So this way it will always do something, it just might not always be the absolute second, the absolute instant that you press spacebar. But we do need to put these in a fixed update, because there's no point in telling you about the fixed update thing and then not actually putting everything in it. And then the only thing that we want in the regular update is that one, actually, the get player input. And then finally, if we go in now, we should have a working jump function. There we go. So all it's doing is it's setting the upward velocity to our jump force. So if we change this, if we make it a lot higher, we're going to be able to jump a lot higher. Obviously, as soon as the player is no longer on the ground, it starts applying gravity to the player. So as soon as there is nothing underneath the player's feet, it starts applying downward velocity. So it's nice and simple. And if we press sprint, we should be able to move faster. And that's our basic player controller. There will be one more video before we get to actually destroying blocks. We just need to do a bit of cleaning up in the world script, and I'm going to add a little debug menu just for the sake of it, so that we've got a way of checking certain values in the game without having to look at the debug console. So there will be one more video before we get to actually destroying and creating blocks, but that will be, I think, the video after the next one. So thanks for watching this. Thank you for all the comments. You guys have been great. It definitely makes me want to carry on making these videos. So hopefully this is as helpful as the last one seemed to be, and I will see you for the next one. Cheers.